Steam locomotives transformed civilization, but they were rolling death traps in disguise. Before modern safety standards, crews operated machines packed with features so dangerous they seem almost deliberately lethal. From scalding steam to crushing couplers, here are 15 dangerous locomotive features that no longer exist. Number 15. Telltale warning devices. Before air brakes eliminated rooftop work, railroads needed ways to warn brakemen of approaching low clearances. Their solution was the Telltale, a series of ropes, chains and leather straps hung from a horizontal bar positioned before tunnels and bridges. When dangling straps slapped a brakeman's face, he knew to duck immediately or face decapitation. Think about that for a moment. The official safety device was literally designed to hit workers in the head. These telltales offered perhaps 2 or 3 seconds of warning before a man standing on a boxcar roof would meet solid stone or steel. At night, in rain, in driving snow, brakemen had to trust these swinging ropes with their lives. The straps would freeze solid in winter, becoming rigid clubs instead of flexible warnings. Some railroads painted them white for better visibility. Others added bells that would ring when struck. None of these improvements changed the fundamental absurdity of the system. The Telltale remained in widespread use well into the 20th century on some lines, long after air brakes should have made rooftop work obsolete. They stand as monuments to an era when worker safety meant giving you a split-second chance to avoid death, rather than eliminating the danger entirely. Number 14. Firebox door mechanisms. Every steam locomotive required constant feeding. Coal had to enter the firebox dozens of times per hour, and each opening of that door exposed the fireman to a blast furnace burning at nearly 2,000 degrees Fahrenheit. Early firebox doors were simple, manual affairs with no heat shielding whatsoever. The fireman would grip a metal handle, swing the door fully open, and shovel coal directly into an inferno while flames licked at his face and arms. But here is where it gets worse. Something called flashback could occur when the door opened. Cold air rushing in would sometimes ignite unburned gases accumulated in the firebox, creating an explosion that blew flames directly at the fireman. Crews called it getting kissed by the dragon, though the results were anything but romantic. Third-degree burns were common. Some men lost their eyesight permanently. The heat in locomotive cabs regularly exceeded 150 degrees on summer days, and firemen would open that door hundreds of times per shift. Automatic stokers eventually reduced this exposure on larger locomotives, and improved door designs added deflectors and shields. But for decades, feeding a locomotive meant repeatedly exposing yourself to temperatures that could sear flesh in mere seconds. Number 13. Single water glass design. The water glass was the most critical instrument in any locomotive cab. This simple tube showed the water level inside the boiler, and if that level dropped too low, catastrophe followed within mere seconds. Early locomotives relied on a single water glass, creating a terrifying single point of failure. If that one glass cracked, clogged, or gave a false reading, the crew had no backup whatsoever. They were essentially flying blind with a bomb beneath their feet. The glass itself was fragile, constantly exposed to thermal shock from the temperature differential between cab air and boiler water. Scale deposits from hard water would accumulate inside, gradually restricting the view or blocking it entirely. Sometimes the connections would clog while the glass appeared to show adequate water, lying to crews about their impending doom. During World War II, American locomotives sent to Britain experienced multiple incidents where crews discovered their water glasses had been giving false readings. The consequences of trusting a faulty glass were absolute. Low water over the crown sheet meant instant disaster, with superheated water flashing to steam at 1,600 times its liquid volume. Modern locomotives required redundant water glasses and tricocks for manual verification. Number 12. Early injector designs. Getting water into a boiler operating at 200 pounds per square inch pressure seems impossible. You cannot simply pour water into a vessel fighting back with that much force. The injector solved this problem using the Venturi effect to force feed water in against steam pressure. But early designs were temperamental nightmares that failed at the worst possible moments. These devices required precise adjustment to function properly. Too little steam, and they would not lift water from the tender. Too much steam, and they would break the vacuum and fail completely. The slightest air leak meant no water flow at all. Crews became experts at nursing these finicky mechanisms, but failure rates remained stubbornly high. When an injector failed, the consequences cascaded rapidly. Without fresh water entering the boiler, the level dropped relentlessly. The fireman would struggle to restart the injector while the water glass showed increasingly dire readings. Sometimes backup injectors failed too, leaving crews racing against time. The truly terrifying failure mode was backflow. A stuck check valve could allow boiler pressure to reverse through the injector, sending scalding water and steam exploding into the cab at over 300 degrees. Improved designs eventually added redundant check valves and better sealing. A locomotive firebox is essentially a steel box, surrounded by water, and held together by more than 2,000 small threaded rods called staybolts. These bolts connect the inner firebox sheets to the outer wrapper, preventing intense steam pressure from blowing the firebox apart. Each bolt bears tremendous stress with every pressure cycle, and failure was invisible until catastrophic. Stay bolts would crack from thermal cycling, corrode from the inside, or simply fatigue after years of service. The danger was that multiple bolts could fail without any external indication. Engineers drilled small telltale holes in each bolt so steam would leak when a bolt cracked, providing an early warning. But scale deposits frequently plugged those tiny holes, silencing the alarm completely. A single failed stay bolt transferred its load to neighboring bolts, accelerating their failure in a cascade. This meant that a firebox could go from apparently sound to catastrophically weak within just days. Inspection required removing the locomotive from service and carefully examining each of the 2,000 bolts. When enough bolts failed, the firebox sheets would bulge inward under pressure, then rupture violently. The crew had no warning. Steam locomotives needed insulation to maintain efficiency and to protect crews from the searing heat of boilers that operated at hundreds of degrees. For decades, the material of choice was asbestos, prized for its incredible heat resistance and low cost. A typical steam locomotive contained between 4,000 and 6,000 pounds of the material wrapped around boilers, steam pipes, and firebox jackets. The problem, as we now tragically know, is that asbestos fibers are microscopic killers. Every vibration of a running locomotive released invisible particles into the air. Maintenance workers removing lagging for repairs breathed concentrated doses. Crews spent entire careers inhaling fibers that lodged permanently in their lungs. The latency period was 20 to 40 years, which meant railroaders who worked around steam power in the 1940s and the 1950s developed mesothelioma and asbestosis in the 1970s and the 1980s, long after the locomotives themselves had vanished. Studies of Finnish locomotive drivers found they had 4 times the normal rate of mesothelioma. British Rail eventually undertook massive remediation efforts, removing asbestos from over 800 preserved locomotives. Every preserved steam locomotive today now carries warnings about potential exposure. Early locomotive cabs offered minimal protection from weather, trackside hazards, and the machine itself. Some designs barely qualified as enclosures at all, with open sides exposing crews to rain, snow, and flying debris at high speeds. But the camelback configuration represented the most dangerous cab arrangement ever devised. These locomotives mounted the engineer's position astride the boiler itself, with the fireman relegated to a tiny exposed platform at the rear. The engineer sat directly above the massive side rods that converted steam power to wheel rotation. If a rod broke at speed, it would flail wildly with enough force to destroy the cab and anyone in it. The engineer had no escape route and no protection whatsoever. Meanwhile, The fireman worked on an exposed platform at the rear, completely separated from the engineer by the entire length of the boiler. Communication between crew members was nearly impossible over the roar of the fire. Hand signals were the only option, and if something went wrong, neither man could help the other. The Interstate Commerce Commission banned new camelback construction in 1927, citing the unacceptable danger to crews. But existing locomotives continued operating for decades afterward. Safety valves are the last line of defense against boiler explosion. When pressure exceeds safe limits, these valves open automatically to vent excess steam and prevent catastrophic failure. They are designed to be tamper-proof for obvious reasons, yet throughout the steam era, crews routinely defeated them. The temptation was understandable. A locomotive working hard on a grade needed every pound of pressure to maintain speed. Safety valves lifting meant wasted steam and lost power. Some engineers would tie down the valve lever or tighten the adjusting screw, buying extra pressure at the cost of catastrophic risk. The first fatal American locomotive explosion resulted from exactly this practice. In 1831, the fireman aboard the Best Friend of Charleston grew annoyed by the noise of venting steam and sat on the safety valve to silence it. The boiler exploded, killing him instantly. In 1912, the San Antonio explosion killed 26 people when an inexperienced worker tightened safety valve settings on Locomotive 704 during routine maintenance. The boiler detonated with enough force to hurl debris and blocks away in every direction. Railroads responded with locked valve covers and criminal penalties. But the practice persisted wherever supervision was lax. Number 7. Rooftop manual braking. Before George Westinghouse invented the air brake, stopping a train required human beings to physically apply brakes on each car individually. Brakemen would ride atop moving freight cars, waiting for the engineer's whistle signal. When it came, they sprinted across swaying rooftops, leaping between cars, and furiously turned brake wheels to slow the heavy train down. Picture this nightmare scenario: a freight train rolling at 30 miles per hour through darkness, rain, or a blizzard. Men running across narrow catwalks on top of boxcars, turning heavy wheels that resist with 50 pounds of force, all while the train bucks and sways beneath them. One slip meant falling between cars or off the train entirely. In the 1880s, Scribner's magazine reported that 1,000 brakemen died and 5,000 were injured every single year, mostly from falls. Brakemen who lasted 7 years on the job were considered exceptional survivors. The work continued in all weather conditions, and frozen brake wheels in winter made the job even more lethal. When a brakeman fell, the train simply continued without him. The Safety Appliance Act of 1893 finally mandated air brakes, but railroads dragged their feet. The deadline was extended twice as brakemen continued dying. Number 6. Link and pin couplers. Connecting railroad cars before automatic couplers meant standing between two moving rail cars with a heavy iron link in one hand and a pin in the other. The brakeman would guide the link into a pocket on one car while signaling for the other car to roll closer. When the pockets aligned, he dropped the pin through to complete the connection. Get the timing wrong by half a second and the cars would crush together, with your hand, arm, or entire body trapped between them. This was not rare. Between 1877 and 1887, coupling accidents accounted for 38% of all rail worker injuries. Mangled hands and missing fingers were so common they became the badge of experienced switchmen. Hiring offices actually sought applicants missing 1 or 2 fingers, considering it proof of experience rather than disability. The link and pin system had no standardization whatsoever. Links came in various sizes, pins had different diameters, and cars might not even align properly. Brakemen spent hours trying to match incompatible equipment while standing in the danger zone between cars. When Eli Janney's automatic coupler became mandatory under the Safety Appliance Act of 1893, coupling accidents dropped from 11,000 in 1892 to just over 2,000 by 1902. Number 5. Early straight air brake systems. George Westinghouse's first air brake of 1869 was revolutionary, but contained a fatal flaw. The system used compressed air directly from the locomotive to apply brakes on each car through a continuous pipe. When the engineer activated the brake valve, air pressure pushed pistons that engaged brake shoes against the wheels. Simple, effective, and absolutely deadly when something went wrong. The problem was a failure mode. If the brake pipe ruptured or a coupling broke, all air pressure escaped immediately. The brakes would release entirely, leaving the train completely uncontrollable. A runaway on a mountain grade meant certain disaster. Trains would accelerate until they derailed on curves or slammed into obstacles at the bottom. The straight air system also responded slowly on long trains. Air had to travel the entire length of the brake pipe before rear cars began slowing, creating dangerous slack action as front cars braked while rear cars continued pushing forward. Westinghouse recognized these flaws and invented the automatic air brake in 1872, which used air pressure to hold brakes open instead of closed. Loss of pressure now meant automatic emergency braking throughout the train. But railroads resisted additional costs for decades. Number 4. Fusible plug failures. The fusible plug was elegantly simple, a threaded plug in the Firebox crown sheet with a core of low-melting alloy. If the water level dropped dangerously low and the crown sheet began overheating, the alloy would melt before the steel failed, releasing a jet of steam that extinguished the fire and alerted the crew to danger. At least that was the theory. In practice, fusible plugs accumulated scale on their fireside surface, just like every other Firebox component. This mineral buildup insulated the alloy core from the heat it was supposed to detect. A scale-covered plug might not melt until temperatures far exceeded safe limits, or might not melt at all. The 1977 Bitterfeld explosion in East Germany killed 7 people, when investigators discovered afterward that the fusible plugs had been so encrusted with scale they were completely non-functional. The locomotive had been without water for at least 4 minutes, enough time for the crown sheet to reach 1,365 degrees Fahrenheit before failing catastrophically. Proper maintenance required removing and inspecting fusible plugs during every boiler wash, but the practice was frequently neglected. Many railroads considered these plugs backup devices and focused on water glasses instead. Number 3. Exposed reciprocating motion. Unshielded connecting rods and valve gear. Steam locomotives convert linear piston motion to rotary wheel motion through an elaborate system of connecting rods, side rods, and valve gear that operate at tremendous speed and force. On most designs, this machinery ran completely exposed alongside the boiler, visible and accessible while running. The accessibility was intentional because crews needed to lubricate bearings and inspect for wear. But exposed running gear created a lethal hazard for anyone near the locomotive. A broken rod at speed became a massive steel flail, capable of destroying anything in its path. The side rods on a large locomotive might weigh several hundred pounds each and rotate hundreds of times per minute. If a bearing seized or a rod cracked, the result was explosive mechanical failure. Broken rods have punched through cabs, killing crews instantly. They have derailed locomotives by jamming between wheels and rails. On camelback locomotives, the engineer's cab sat directly above this machinery, making rod failure almost certainly fatal for whoever was operating the throttle. Modern safety protocols require protective shielding, but steam-era locomotives typically ran with everything exposed. Workers oiling bearings on running engines risked being caught in the machinery. A locomotive firebox operates under negative pressure, with the draft from the exhaust pulling air through the fire and hot gases through the boiler tubes. This only works when the locomotive is working, with exhaust creating suction. When the throttle closes, the draft stops, and conditions become perfect for blowback. Blowback occurs when atmospheric pressure suddenly reverses the flow of hot gases through the boiler tubes. Instead of being pulled toward the smoke box, fire and superheated gases blow backward through the firebox door into the cab. The trigger might be entering a tunnel where pressure waves reflect off walls, or simply closing the regulator without opening the blower valve first. The result is a jet of flame erupting from the firebox door directly at the crew. In 1953 and 1954 combined, British Railways recorded 46 blowback incidents, resulting in 52 injuries and 1 fatality. These were not rare events, but routine hazards that crews learned to anticipate through painful experience. Severe blowbacks could burn exposed skin in seconds and ignite clothing instantly. The technical solution was simple. Always open the blower before closing the regulator to maintain artificial draft. But a moment of inattention could transform a locomotive cab into a furnace. Number 1. Crown sheet failures. The crown sheet is the steel plate forming the top of the firebox, constantly heated from below by 2,000-degree fires and cooled from above by boiler water. As long as water covers this sheet, heat transfers safely into steam production. But let that water level drop just a few inches, and the crown sheet becomes a ticking bomb. Uncovered crown sheet steel heats rapidly to temperatures where it loses structural strength. At 1,200 degrees, steel becomes plastic and can no longer resist boiler pressure. The crown stays that hold the sheet in place can pull through, like pushing fingers through wet cardboard, and thousands of gallons of superheated water at 386 degrees and 200 pounds pressure flash instantly to steam. Water expanding 1,600 times its volume creates an explosion equivalent to hundreds of pounds of dynamite. Boilers have been launched completely off their frames and hurled hundreds of feet. In San Antonio in 1912, a locomotive boiler explosion killed 26 people and hurled debris 7 blocks in every direction. Crown sheet failures leave no survivors in the cab. The explosion is instantaneous and absolute. The crown sheet was the most lethal single component on any steam locomotive, punishing any lapse in attention with immediate death. And that's all, folks. These features show that progress in railroad safety was literally written in blood, with each improvement representing lessons learned at terrible cost. If you enjoyed this journey, please hit subscribe. Here is another video I have selected for you. See you next time.